Good afternoon. I welcome you all to this session of fluid mechanics. We are discussing about the different types of parallel flows. Now, today we will be discussing another type known as Hagen-Poiseuille flow. Let us concentrate here, Hagen. So, now we will discuss Hagen-Poiseuille flow. We have discussed the plane Poiseuille flow in the last class. Names of the two people who developed the equations for this flow, after their name, this Hagen-Poiseuille flow. This is basically flow through a circular tube. So, if we consider like this, a circular tube like this, or rather we just, so this is a Hagen-Poiseuille flow, the flow through I am sorry. So, we can just change this. So, this is not good. So, we can change it, we can make it again Hagen-Poiseuille flow. I am sorry, we can make it again Hagen-Poiseuille flow. This designates the flow through a tube, circular tube. Let this is the flow through a tube of circular cross section. So, this is the flow. So, this is the axis. So, here similarly, if we first we fix the coordinate axis for all types of flow, we fix the cylindrical polar coordinate, that means Z. From here we measure Z. Any point we measure at R and an azimuthal location, that means if this be the R, this location be the R here, this is the surface, not here, here R. So, this is the azimuthal location. That means R, theta, Z are the coordinate. R is the radial coordinate. At the surface, it is capital R. That means this one is R, capital R, the radius of the circle. Any point has got a radial coordinate R from the axis. This is the Z in this direction, and theta is the azimuthal direction. So, these three coordinates, as you know, defines the cylindrical polar coordinates compatible with the geometry. Flow through a cylinder, tube of circular cross section. Now, again if we consider a parallel flow, fully developed incompressible laminar flow, which is already told, fully developed, I also write. The meaning of this is not totally appreciated at this moment. Fully developed laminar, steady, all these things are there, steady, incompressible flow. Incompressible flow. All right. Now, when it is a parallel flow, definition wise here we define Vz naught is equal to 0. The flow is always in the axial direction. There is no component of velocity in the radial or in the azimuthal. That means tangential direction. That means Vr is 0, Vr and V theta all 0. So, as far as our routine application, if we write the incompressible flow continuity equation in cylindrical coordinate system, if you recall, del Vr del R plus Vr by R plus 1 by R del V theta del theta plus del Vz del Z0. Okay. Vr, V theta, Vz are the Vz Z direction velocity, Vr is R direction velocity, and V theta is theta direction velocity, tangential velocity, azimuthal direction. But incidentally they are 0 for parallel flow. So, continuity equation, that is divergence of the velocity vector in cylindrical coordinate, stands like that, as I told you earlier while discussing continuity equation. Now, V are 0, V theta 0, only one component of velocity exists, and as is consequence, usual consequence, that means Vz is not a function of Z, because del Vz del Z 0. Another thing we have to consider here, that the flow is symmetrical about this axis, symmetrical flow about the axis R is equal to 0, that which means that the flow is azimuthally symmetrical. That means del theta, that means there is no variation of any parameter with respect to theta. All parameters are functions of R and Z we consider. That means with theta there is no variation, del theta of any parameter is 0, which means that any RZ plane at any theta represents the similar flow situations. That means it is symmetrical. Therefore, Vz cannot be, according to this definition, cannot be function of theta. The flow is symmetrical about the axis. So, So therefore only go is that Vz is a function of r, that means Vz is a function of the perpendicular coordinates, coordinates in the perpendicular direction to the velocity. This is the usual consequences, which we found in case of Cartesian coordinate system. U is a function of y, where u is the velocity component in the x direction and only existent velocity component. So here also like that, Vr v theta 0, Vz is a function of r. Now I write Navier-Stokes equations. Navier-Stokes equations, that is equation of motion in r directions. So what is the equation? Rho dvr dt, that is the acceleration minus v theta square by r in r direction, is equal to minus del p del r. If you write this equation, you have to just make practice that now for incompressible flow, so only this Laplacian term will be there, and that in cylindrical coordinate takes this form, del square Vr. One has to develop this habit to write the Laplacian del Vr del r plus 1 by r del Vr del theta plus del square Vr del z square minus Vr by r square. Due to the curvature, these two terms comes 2 by r square del v theta del theta. So these are the terms for the Laplacian, and for incompressible flow this is the r direction Navier-Stokes equation, the equation of motion in r direction. Let us see what does it give. dvr dt 0, there is no Vr. Even if we split it, if one wants to see del Vr del t, the temporal term, plus Vr del Vr del r, convective term, plus that you, as you know, v theta by r del Vr del theta, well, plus Vz del Vr del z. So each and every term is 0, temporal derivative is 0. So Vr 0, del theta is 0, moreover v theta is 0. Though Vz is not 0, but del Vr del z 0, there is no Vr. So therefore as a whole the substantial derivative is 0. There is no v theta 0. All these terms are 0 because Vr is non-existent. So there is no Vr and its gradient, v theta Vr. So therefore the only consequence is that del p del r is 0. So therefore we get del p del r. Again we get from azimuthal symmetry del p del theta is 0. But this del p del theta 0 we can obtain also from Navier-Stokes equations in theta direction, but it is not required now, because unnecessarily we may not write this equation to get del p del theta 0, because we have considered then azimuthally symmetric flow, that if flow is symmetrical about r is equal to 0 axis, del theta of any parameter is 0, that means del p del theta is 0. So only go is this, p is a function of z. Ho gaya, it's complete. So Vz is a function of r and p is a function of this. This you keep in mind. Now write the z direction Navier-Stokes equation. NS equation in z direction. NS equation in z. That means along the axis of the pipe, z direction. Write rho dvz dt. So dvz dt is the only acceleration in z direction, unlike r and theta direction. No cross component come. So this must be equal to del p del z plus mu Laplacian of Vz, that means del square Vz del r square. So Laplacian in the cylindrical polar coordinate, you know the operator is like that, del square del r square plus 1 upon r del r, 1 upon r del r. That means this is operating on Vz plus 1 upon r square del theta square, operating on Vz plus del square del z square, operating on Vz. So this is the Laplacian. Now let us see, this is 0. Why? If you just, now it will be difficult to accept this is 0. Why? Because Vz is not 0. Why dvz dt 0? Let us split it. Then only you will accept. Plus, so this becomes Vr del Vz del r, the convective part, plus V theta by r del Vz del theta, plus Vz del Vz del z. All right. Now it is clear that each and every term 0. For steady flow, this is 0, del Vz del t. Now Vr is non-existent, 0, so this term is 0. V theta is 0 and moreover del del theta of any parameter is 0, it is 0. Now though Vz is non-zero but del Vz del Z is 0 from continuity. So that we write Vz is a function of R because continuity has already told us del Vz del Z 0. For this is 0. So therefore we see all the terms are 0. So dVz dt is 0. Here you see this is not 0. Nowhere we find that this is 0. This is also not 0, but this is 0 because no parameter is a function of theta. So second derivative of theta is also 0. Now this can be neglected with respect to del square Vz del R square. Why? Now del Vz del Z may be 0, but del square Vz del Z square may not be 0. But if we consider del Vz del Z 0, del square Vz del Z square may be 0, but we can argue in a different way that the length of the tube is much more compared to the radius, so that variation in Z direction is neglected compared to that in the R. Mathematically also one can tell if del Vz del Z 0, del del Z of del Vz del Z is also 0. So both ways we can tell this is 0. So therefore we are having with this and this. But it has been proved that P is a function of Z only. So we get rid of del. So we write only D, ordinary differentials. Similarly, it has been proved that Vz is a function of R only. So therefore this is also 0. So therefore Vz del we get rid of D. So therefore I write this first, that d square Vz dr square plus 1 upon R dVz dr is equal to 1 by mu dP dz. A similar equation that we arrived in Cartesian coordinate. There we arrived d square u dy square is 1 by mu dP dx. Here x coordinate is the z direction. That means z is the direction of flow, r is this direction, the radial direction. The governing equation is d square Vz dr square plus 1 upon r dVz. Vz is a function of r, that's why it is an ordinary differential equation, and P is a function of z. With the same argument we can tell that dP dz is constant and left hand side is constant. That means if Vz is a function of r only, so d square Vz dr square can either be constant or a function of r. 1 by r dVz dr is either a function of r or constant. That means as a whole left hand side option is there either a function of r or constant. And since P is a function of z, the option for right hand side is either is a function of z or constant, depending upon whether P is a linear function of z or non-linear function of z. But a function of r cannot be made equal to a function of z. So therefore the equality between the LHS and RHS, the left hand side and right hand side, tells that this is constant and this is constant. They can only match at a constant value, which means that Vz is a quadratic function of r, so that this gives constant value independent of r, and P is a linear function of z, so that this gives a constant value. That means dP dz is constant. Now you just integrate it. How to integrate? You write in this fashion by multiplying r. This is a simple calculus differential equation. So there is nothing fluid mechanics in it. If you just multiply r, so you get r d square Vz dr square plus dVz dr, which can be written as dVz dr. That means if you multiply r on both the sides, I get this. Multiply r d square Vz dr square plus dVz dr. That means r d square Vz dr square plus differentiation of r is 1. That means I can write then by multiplying with r left hand side like this. Then what I can do? I can integrate this. So if you integrate this, first line will be r dVz dr is equal to 1 by 2 mu dP dz r square, very simple, plus C1. So second integration give dVz dr. Now this will be C1 by r and this will be again r. That means 1 by 4 mu dP dz into again r square, because this will be divided. So r square by r, that means r dr again r square by 2, 4 mu, plus C1 by r will give you C1 ln r, C1 by r dVz dr, second integration C1 another integration constant C. So therefore, I am also playing like Saurabh, Vz is 1 by 4 mu, then integration gives Vz is 1 by 4 mu dP dz r square plus C1 ln r plus C2. Alright, very good. So this is the differential equation. Now you tell me what are the boundary conditions to find out C1, C2. You must have a look to this, that this is the picture. What are the boundary conditions? You tell me the boundary conditions. That means if I keep it like this, what are the boundary conditions? This is the flow. So what are the boundary conditions? So boundary conditions at R is equal to R, what? Vz is equal to 0, but one boundary condition. Then what to do about C1, C2? At R is equal to 0, very good. Tell me, at R is equal to 0, del Vz del R is 0. Because this is symmetrical about this axis. But this is not required vigorously. Mathematically, one can simply argue that at R is equal to 0, the flow field is defined. So this term cannot exist, because this term cannot define the equation physically at R is equal to 0. It is undefined with an ln r term. So C1 is 0. Or if you tell that R is equal to 0, both way we can tell. This is physically we can eliminate this term, or we can eliminate this term mathematically also by telling that since it is symmetric about R is equal to 0, so del Vz del R, that means the derivative has to be 0 with a maximum or minimum at R is equal to 0. And mathematically if we look that dVz dr, R dVz dr, just the previous step before integration is this. So at R is equal to 0, dVz dr 0 means C1 0. So either way we can tell C1 0. So from this equation precisely we get C2. And finally what we get is Vz is equal to, after having this R square by 4 mu, because this is the value of C2 dP dz. So minus dP dz, I always write like this, into 1 minus R square by R square. This is precisely the velocity distribution equations. And this is a parabola. That means if you draw it, again I am drawing this, that means if you draw it, so it is a again sort of parabola. It has to be a parabola. We have seen the quadratic equation. This is known as Hagen-Poiseuille equation, or simply Poiseuille equation. If the word plane, the adjective Hagen-Poiseuille equation. Plane Poiseuille equation is the equation velocity distribution between two fixed plates. So either Hagen-Poiseuille or Poiseuille equation. This is the velocity. Poiseuille equation or Poiseuille velocity distribution, or Hagen-Poiseuille velocity distribution. The word Hagen-Poiseuille or only Poiseuille without any adjective means that it is the equation for a parallel flow through a pipe or through a duct of circular cross section, through a cylinder. So the velocity distribution is this, Vz R square by 4 mu minus dP dz, 1 minus, so again I write Vz R square by 4 mu minus dP dz into 1 minus R square by R square. Where is Vz maximum? At R is equal to 0. So maximum Vz is R square by 4 mu minus dP dz. Another thing is clear, that the sign of Vz represented by sign of dP dz. When dP dz is 0, Vz is 0. That means flow is entirely governed by the pressure gradient. A negative pressure gradient causes a velocity in the positive z directions and vice versa. Obviously, it has to be that this is the z direction. A positive Vz means the negative pressure gradient. That means pressure here is higher, pressure here is lower. And the opposite is also true. And if dP dz 0, Vz is 0. Now question comes, how to find out average velocity. That means first of all we will have to find out Q, because we know average flow velocity is Q by area. What is the definition of average velocity? Vz average is Q by area. So what is Q? How to define Q? So to define Q, what we have to do, we have to consider an elemental ring at a distance r. At a distance r, an elemental ring, you understand, of thickness, the thickness dr. Here better if I write like, if I draw like this, okay. You consider an elemental ring. this is the circular cross section here at any radius r, that at any radius r you consider an elemental ring of thickness dr. That means this is the radius r. We consider an elemental thickness here dr and find out what is the flow rate through these annulus. Flow rate through these annulus is the u or Vz here, Vz at that r which is a function of r given by this, into what is the area of this annular ring, twice pi r dr. So simply integrate it 0 to r. This is capital R, that is the radius. So therefore, if I write pi, so Q is this, Q is this. So what is Vz average? So Vz average is, I like to show you what I told you the last class, that Vz average is Q by A. That means 0 to r, now twice pi I can take. So Vz as a function of r into r dr divided by pi r square. So is equal to 2 by r square 0 to r Vz r dr. So you see it is not a simple arithmetic mean, it is an weighted average Vz into r dr, not Vz dr by into 2 by r. This could have been the arithmetic average. In this case, it is not an arithmetic average. Another typical weighted average 2 by r square Vz r dr. So how do you know that this type of average will be there? This depends upon the geometry. Because we know the basic definition of Vz average is Q by A. So simply we define Q and then divided by area, we can define the expression for the average velocity. Here it is not like that u dy divided by 1 by h. So it is not Vz dr divided by 1 by r. Rather it is Vz r dr 2 by r square. That means it is a typical average, weighted average Vz into r dr, which has come from the definition of the flow rate. I am sorry, this is capital R, this has to be capital R square. Very good. All right. Now we find out the value of Q. If we substitute this Vz r, that is a function of r, that means this function if you substitute with 2 pi r dr, 2 pi you take out and you find out the integration, do the integration, you will find that Q becomes equal to r square by 8 mu into minus dp dz into pi r square, rather I write pi r4. This is the value of Q. If you solve this integration, that means it comes Q is equal to twice pi integration of 0 to r, Vz as a function of r into r dr. That means that function of r you substitute. What is that? Vz is equal to r square, which we have got as Hagen-Poiseuille velocity distribution, minus dp dz into 1 minus r square by r. That means if you substitute this, integrate, you get this. So therefore Vz average as Q by pi r square, that is the cross sectional area, is simply pi r square by 8 mu minus dp dz. The relationship with the Vz maximum is Vz max by 2. Maximum is pi r square by 4 mu. If you recall the maximum velocity we got as pi r square by 4 mu, Vz maximum, yes, r square by 4 mu minus dp dz. So pi is not there, r square by 8 mu dp dz. Vz maximum is r square by 4 mu minus dp dz. हो गया? All right. Vz average r square by 8 mu minus dp dz. Tau. We are interested now, tau wall, shear stress at the wall. That means is equal to tau at r is equal to r. It is minus mu dvz dr. dvz dr is the velocity gradient and that is equal to the shear rate. Why minus sign I am writing here? Can you tell? Why minus dvz dr at r is equal to r? This is because here the coordinate axis has been chosen in such a way that that r is measured from the axis and the velocity if you see here the velocity, I think it will be a better figure here. If you see here that the velocity profile is such that the velocity is decreasing with the increasing r. That means r is not measured from the solid surface. Solid surface always velocity is 0 when the solid surface is at rest, that is the no slip condition. So velocity must increase from the solid surface, and always the normal coordinate should be measured from the solid surface. We will see afterwards. We define some wall coordinate or normal coordinate from the wall which is perpendicular to the wall along outwardly. But here in this conventional cylindrical coordinate, the r is measured from the center. So an increasing r shows a decreasing velocity. To make account for this, we make conventionally a minus sign in defining tau. So now rest part is the simple mathematics. So dVz dr, what is Vz? Better I write Vz also, so all at a time. Space is so small here, 4 mu minus dp dz into 1 minus r square by r square. So what is dVz dr? dVz dr is, now it is twice r, and r is equal to r means it is twice r square. Let us write. So r square 4 mu minus minus cancels, dp dz into 2r r square, and 2r means at r is equal to r, 2r. That means r square cancels. So it is r by 2 into dp dz. All right. So therefore r by 2, I am sorry, 2 mu. So therefore tau wall is minus mu, so mu will cancel. So r by 2 minus dp dz. So this is the value of wall shear stress. Rather, we should make it in terms of the Vz average. That means r by 2 into 8 mu Vz average. You understand? 8 mu Vz average by r square. That means I just substitute dp dz in terms of the Vz average. That means tau w becomes is equal to 4 r mu Vz average by, I am sorry, 4 mu Vz average by this cancels r. So this is the expression of tau w in terms of Vz average. That means minus dp dz is Vz average 8 mu by r square. So this is Vz average 8 mu by r square. So Vz average 8 mu by r square. So r cancels. So 4 mu Vz average by r. Now what is the next step? Next step is skin friction coefficient, Cf. So Cf is defined as tau w by half rho Vz average square. Okay, if you do that, you get an expression. You can see it 16 by rho Vz average into 2r. So actually it is 8, I just multiply divided by mu. So this rho Vz average, 2r is diameter of the tube, d by mu is equal to Reynolds number for flow of fluid through circular duct, through a cylindrical duct, circular cross section through a cylindrical duct. The Reynolds number is defined. Rho, the characteristic velocity is Vz average, that is flow rate by cross sectional area, times the diameter of the tube, which is the hydraulic diameter, dh 4a by p, cross sectional area by weighted perimeter, 4 pi d square by 4 divided by pi d. So it is simply d. So this is the definition of Reynolds number. We will come again. So therefore Cf is 16 by Reynolds number, which is very important, that in a pipe flow, that Hagen-Poiseuille flow, Cf is 16 by Reynolds number. It is inversely proportional. In case of plain Poiseuille flow, it was 12 by Reynolds number. Cf is 16 by Reynolds number. So Reynolds number definition is rho Vz average d by mu. All right. So this is about the Hagen-Poiseuille flow, all aspects of Hagen-Poiseuille flow. All right. So, any queries? So, today, well, I will leave here, and thing is that next class we will start a new chapter, that is the viscous flow through pipes, the application of viscous flow. So, about the exact solutions, I just like to make a brief closure before ending this section, that today we started, this class we started with the derivation of viscous momentum equations or equation of motions for a viscous flow, and we first recognized that for a fluid at rest the only stresses are the pressure, the normal stresses which are compressive in nature and same from all directions, the Pascal's law. For an ideal fluid flow, we have considered that if we take a fluid element, the only surface forces are the normal forces, which are thermodynamic pressure or static pressures. But for a frictional fluid or viscous fluid, along with the normal forces, there are shear stresses. So therefore, if we recognize the external forces, apart from the body forces, the surface forces consist of both the normal stresses and the shear stresses for a viscous fluid. So then we developed the equation of motion, that means we equated the mass time acceleration with the external forces. We wrote the external forces in terms of the stress components. The most vital part is the relationship between stress and the strain rate components if we want to express the equation of motion in terms of the velocity components and the pressure, which we did not do in this class, but we recognize the different assumption based on which stress and strain rate relationship is developed and finally accepted the relations. The assumptions were like that: the fluids behave in such a way that the relationship between stress and rate of strain are linear, and there is a class of fluids which behave so and known as Newtonian fluids, whose stress and rate of strain behavior or relationship is linear. This has been found experimentally, and this relationship is invariant with coordinate transformation. Another assumption was that the fluids for which the equation of motions will be developed, they are viscous fluids, but their second coefficient of viscosity is 0. And another assumption, last assumption, was that the equation of motion will be derived in such a way the continuity to hydrostatic should be there. That means you see the equations of motion, that is the Navier-Stokes equation, if you put all u v w 0, you get the equations of hydrostatics. If you put mu is equal to 0, you will get the Euler's equations. So all continuity are there to non-inviscid flow, frictionless flow, and even for the hydrostatic cases. Okay. So therefore we will see that the continuity is there. So based on this, the stress and strain rate relationships were developed, and finally these were substituted. You got the equations of motions in terms of the velocity and pressure, and these equations are known as Navier-Stokes equation, named after the two persons Navier and Stokes. Then we recognize the nature of the Navier-Stokes equation, that it is a partial differential equation. Definitely u, v, w being the dependent variables are functions of x, y, z and t. There are 4 independent parameters x, y, z and t, and there are 4 dependent variables u, v, w and pressure. We have 4 equations, 3 equations of motion in 3 coordinate directions, and 1 is the equation of continuity, so they can be solved. So now the nature of the equation is they are partial differential equation, their order is 2, second order is governed by the viscous term, Laplacian term. Then the about the linearity and non-linearity, it is a non-linear equation, because if you see the acceleration part, it is the convective acceleration which is non-linear in nature. U del u del x, v del u del y, this gives the power of 2 for the dependent variable velocity component. So as a whole, the Navier-Stokes equation is a non-linear second order partial differential equation, which do not have a closed form solutions. But there are certain cases, simple cases of flow, where we have exact solutions, closed form solutions of Navier-Stokes equation. In those simplified cases, by the physics of the problem, the basic Navier-Stokes equation, which is non-linear second order equations, are being transformed to a very simple ordinary differential equations, even second order, but linear ordinary differential equations. Those cases are parallel flows, and we discuss the solutions of some parallel flows, Hagen-Poiseuille flow, Payne-Poiseuille flow and Couette flow. That was the coverage of this section. Thank you.